All right, welcome to lecture 2. A lot of you guys, quick raise of hands. How many people believe themselves to be registered for this course? Okay, it's like a good number. Cool. So maybe sort of a quick administrative note before we dive in. So the first problem set is out. If you are on the Slack, you have been notified of this. And also if you go visit the course website, you can download the first problem set. It's due in 2 weeks on Gradescope. If you are not on the Slack, you should send me an email and I will add you to the Slack. Everyone feel comfortable in their ability to find the problem set, do it, and then turn it in on Gradescope in 2 weeks. Awesome. Like a competent class. Okay, so first order of business. As you recall, there was, homework 0 was to participate in this guess 2/3 the average game from last class. As of 8 a.m. this morning, I tallied the results. I gather it doesn't include absolutely everybody, but we'll see how you did. As of this morning, the average, and remember the rules, right? You have to enter a number. It doesn't have to be an integer between 0 and 100. We had a web form for this. What I was going to do is compute the average. It was a little over 13, and your goal was to try to be closest to 2/3 of the average. Okay, so the average was a little over 13. 2/3 of the average, if I've done my math right, was a hair over 9. Someone guessed 9.11, which was the winner. Jack, is Jack in the audience? He says he's gonna be 10 minutes late. I've got $5 for him, but okay. Let me know when he enters. What is your name? When Jack enters, can you just shout out here's Jack, and I'll handle. Okay. Okay. So I just want to think a little bit about this game. Okay, and then on the homework you'll see you have to prove something about it. But if you think about this game, right, the strategy space is you enter a number between 0 and 100, right? So the average, even in the worst case, where everyone doesn't think about this game at all and they enter the largest possible number, 100, the average can't be, of course, bigger than 100, and so 2/3 the average can't possibly be bigger than 66. So it would just be a mistake to have entered a number bigger than 66. That is, when we see the definition today, that is what we will call a dominated strategy. If you entered something bigger than 66, that was just a mistake. You should have lowered your guess, and that could only have done better, even if everyone else in the class was maximally stupid and entered 100, right? So entering something above 66, that's just a failure of your own rationality, independent of what you think other people are going to do. Okay, good. Nobody did that as of this morning. Now you can go another level down. You can say, okay, well, I'm pretty smart. I know that a winning answer is going to be below 66, but I don't know about all of those other people in the class. Maybe they're all super dumb. They're going to enter 100, in which case you might, 66 is not an impossible answer. You could win entering 66 if everyone else entered 100. Or you might think, this is a class at Penn, these kids are pretty smart. They're probably going to have realized that there's no way to win by entering something 66 or higher. So nobody's going to enter anything. I think nobody in this class is going to enter something above 66. And if that's true, of course, then the average can't be higher than 66. And so 2/3 the average can't be higher than 44. And so, okay, nobody entered a guess above 44 either, which means not just are you guys reasonably clever, but you think that your classmates are reasonably clever as well, at least at one iteration. Now, of course, if you think that all of your classmates have gone through the same chain of logic that you have, right? None of them are going to enter a number above 44. You might think, okay, well, the average can't possibly be above 44 if they're, at least one, level depth cleverness. In which case, like, if that were the case, nobody would enter, either there wouldn't be a winning guess above 29 1/3. Okay, we did see, now we're starting to see some guesses. We did see one above that, which is not right. The person who entered this, it's not that they've, right, it's not that they're not smart, it's that they think you guys aren't as smart as they are, right? And you can keep going, right? Like the number of you who think that you're gonna continue this the number of you who think that your classmates are gonna continue this logic, at depth 4, okay, it's growing, right? At depth 5, it's even larger. And of course, you might have thought that your classmates were all maximally rational, right? That we would sort of continue this induction all the way down to 0, right? I mean, eventually, if everyone's like maximally rational, and assumes that their classmates are, and assumes that their classmates assume that they are, and assumes that their classmates assume that, each other, so on and so forth. It's kind of like the Islanders problem you guys thought about. Really, the only winning guess can be 0. And 3 of you thought quite well of your classmates, but of course, they didn't win. Okay, so anyways, when Jack enters the room, I've got $5 for him. This is maybe just to sort of, we're going to talk about iterated elimination of dominated strategies today. And this is just maybe to get you thinking about, whether we really believe the predictions that it makes. Okay, so that was the game we played. Any questions about this? Okay. So what I want to do today are, if you've taken a game theory class before, review many of the basic definitions of game theory that are going to underlie sort of what we do this semester. And if you haven't taken a game theory class before, maybe you're seeing them for the first time, but they're not that complicated, so it'll be fine. Okay. So we're going to talk about games and what they are. We're going to talk about what a best response is. We're going to talk about what a dominant strategy is. And we're going to talk about iterated elimination of dominant strategies, which is the kind of logic that you might go through, similar to how you might think about how you'd play this guess the 2/3 the average game to try to make predictions about what maximally rational opponents might do. And we'll talk about solution concepts. There's going to be a bunch of solution concepts, like if you get really lucky, everyone has a dominant strategy. We can talk about dominant strategy equilibria. We can talk about, if you get marginally lucky and there's a unique solution to this sort of iterated elimination of dominated strategies kinds of ideas. And we'll talk about Nash equilibria and the relationship between these things. And this will be sort of the beginning of what will be sort of a longer theme in this class of thinking of hierarchies of solution concepts that try to make fewer and fewer assumptions. Okay, so that's the plan for today. Any questions about the plan or course logistics or when Jack is going to arrive or anything like that? Okay, so okay, it's a game theory. Like we're already on lecture 2. I better tell you what a game is. So what's a game? So a game is going to be, a model for an interaction, but really some mathematical object that's going to be defined by a few things. Okay, what are those things? First, there's a set of players. Okay, think of this as a finite set for now. The players intuitively are the agent that will be interacting in the game, whatever that means. I'll write P for players. Now, if it's an interaction, the players had better be able to do things. And we will give a name to the set of things that each player can do. Okay, so we'll call that the action set for each player. Okay, the action set for player I for some, let's imagine the players are just like indexed by integers or something. So we can say player 1, player 2, player 3, so on and so forth. the action set for player I will write AI, and think of that as just some finite abstract set for now. It could be like rock, paper, or scissors, or any other set of actions, depending on what the game is. The name of the actions don't really matter, right? But their cardinality does. And it's going to be convenient for, like, we're going to have to talk a lot when we talk about games about sort of what I'll call like a game profile, which is like the set of actions chosen by all of the players. Okay, so like, when we start talking about game dynamics, players will be choosing an action. Each player will choose an action, an element of their set AI. If we have n players, they're all going to do that. And it's going to be convenient for us to think about the vector of actions, like this n tuple of actions that corresponds to the choice made by each of these n players. Okay, and just to like introduce some notation, the space that will live in, like this vector of n actions, this like action profile, a choice of an action, one for each of the players, I'm going to call that A. And it's just the Cartesian product of the action set for each of the n players, which just means, what kind of object lives in A? Well, it's a vector. The length of the vector is equal to the number of players. Every player I has their own coordinate in this vector. And what the vector records in coordinate I is just the action chosen by player I. Okay. More notation. It's going to be, since we're talking about like strategic decisions by players, it's going to be handy for us to talk about, when we zoom in on some particular player I, we're going to have to like think about what action should she choose, what should player I choose, given what everyone else in the game is doing. So it's going to be handy for us to zoom in on particular players and talk about the choices that all of their opponents are making. Okay, so when we zoom in on player I, what will be of interest to her when she is choosing what action to take is the set of choices, the set of actions chosen by the n-1 other players other than her. Okay, so what does that object look like? It's a vector of length n-1 rather than n. It has one entry for every player other than her. Right? She hasn't made her choice yet. Okay, and the space that those vectors live in, I'll call that A minus I. The notation is sort of meant to evoke that I am excluding player I. And what is that space? It's just the Cartesian product of the action set, AJ, for each of the players J other than player I. So a vector, an action profile in A minus I, what does it do? It specifies an action for everyone other than player I. Player I's action is undetermined by an action profile in here. And what kind of object is it? It's a vector of length n-1. It's got a coordinate belonging to every other player J. There's n-1 other players J. Okay, so that's notation, but I'm going to use it a lot. So if you have no idea what it could possibly mean, please ask now, because otherwise the class will be extremely painful for like the next semester. So notational questions? Okay, good. And okay, finally, like, the basic premise in game theory is that people will be trying to choose actions so as to maximize their own utility. And so to specify a game, in order for that to even begin to make sense, I need to be able to tell you what are the preferences of each of these players, what maximizes their utility. Now, what are the kinds of things that players can have preferences over? Well, the only thing we've defined is that players are going to choose actions, and a state of the game corresponds to a choice of action for each player. That's this thing that I'm going to call a play profile that lives in this space A. And so that's what players care about. So a utility function for player I, and each player will have their own utility function, maybe a different one. People's people's objectives can be different, is just some function labeling every possible action profile with a real number, which you should think of as saying, okay, how happy am I, if the way things shake out are that we're playing some action profile little a. Okay, so for each of the exponentially many ways that the n players in this game might choose their action, right? There's exponentially in n many different combinations of choices. The utility function tells you numerically how happy player I is with those actions. Okay, so this is just some function mapping A, the set of action profiles, to real numbers. Okay, makes sense. Okay. So the basic premise in game theory, and of course this doesn't make sense yet. We're going to have to unpack different ways you can try to formalize this premise and what predictions mean. But the basic premise is that players are going to act so as to maximize their own utility. Okay, so my utility function in a game sort of guides somehow how I'm going to play the game, and I'm going to try to play the game, whatever that means, so that I get a big number out of this utility function. Now, I only, the utility function is a function of what everyone else does. I only directly control what I do, not what everyone else does. So, I can't just unilaterally assert that the state of the world is going to be the thing that maximizes my utility. I can make choices for myself, but I can't control what others do. Okay, but my basic goal is going to be to try to maximize my utility. Is that clear? And so we can try to formalize that a little bit. I mean, of course, I can't, it doesn't make sense to directly maximize my utility, because my utility is a function of things that I do not control. But, if somehow everyone else told me what they were going to do, then it would make sense to think about the thing that I could do, the action that I could choose that would maximize my utility. Jack?
Yes.
Oh,
I heard I won.
you won $5. Yeah, so you can count it if you want.
I trust you.
Okay, I hope this buys a good teaching review at the end.
Hopefully.
Okay. Okay. Good guess. So you were supposed to tell me when Jack walked in. Okay, so it doesn't make sense to maximize my utility from whole cloth, because my utility depends on things that I don't control. But if I knew what everyone else was doing, then maximizing my utility would be a well-defined problem. Okay, so here's a concept that's going to be core to lots of what we talk about. It's what's called a best response. So suppose me, player I, knew what actions all of my opponents were taking. Okay, so I knew the sort of action profile that I'll write little a minus I, which lives in this space I just defined big A minus I, which remember is a vector of length n minus 1 that tells me the actions that are chosen by all of my opponents. Okay, then my best response to that set of actions, the action profile of my opponents, would be to choose the action AI that maximizes my utility given what everyone else is doing. Okay, and just sort of sneaking in another bit of notation here. Remember, the utility function takes as input a vector of length n, specifying a choice of action for all n players. What we've been given here, the object that we are best responding to, we are defining a best response with respect to, is a vector of length n minus 1. Specifies the actions just for the n minus 1 other players. But if I have an action A for player I and an action vector A minus I for the n minus 1 other players, I'm going to just write A comma A minus I to stitch those together into a full action profile specifying an action for all n of the players, the n minus 1 other players, and me. And that's a thing that I can plug into a utility function. Okay, and so the best response to the choice of actions of my n-1 opponents is defined to be just the action that maximizes my utility when I plug it into my utility function together with the choice of action for the n-1 other players. Does that make sense? Okay, so yes, so like, our basic premise, agents are going to try to act so as to maximize their utility. Okay, we have to like think about what that means, but like, we're going to start thinking a lot about best responses. Maybe if people are playing well, then I should be best respond. I'm not going to necessarily get to the game state that is my absolute favorite. Okay, I can't control what other people do, but I can control what I do. So maybe I should be best responding to what everyone else is doing. And maybe other people should be doing the same. Yeah. Yes, so we could just be given one. I could say like, here's an action profile. It lives in this space, capital A. Or if I'm given an action, sort of this sort of partial action profile that specifies the action of everyone else other than player I, and then I'm also given, maybe I should have written like a little I here. If I'm also given an action for player I, when I just write something like this, you interpret that as, stitching in the one missing coordinate of a minus I in the right place. And together, this specifies an action for all n of the players. Does that make sense? Good question. Okay. Okay, so nobody has asked this yet, but last semester, someone asked this, and it was a pretty good question, right? I sort of say, okay, like, here are the basic axioms that we are going to like base the rest of the course on. People are just going to like single-mindedly maximize their utility. You can ask, okay, like, is game theory just for like sociopaths? Like, is there no? I'm just like, am I modeling like only like hedonistic agents that care only about like their own like well-being and not like anyone else? And the answer is no, right? Like, I have made no presumptions at all about what your utility function is. Your utility function could be anything, right? Like in choosing to model some interaction, if you want people to sort of, have high utility when everyone in their city is well-fed and well-housed, that's fine, right? Like there's nothing saying that your utility function has to take large values for states of the game that sort of correspond to you getting stuff or whatever, right? Your utility function could be anything. The utility function is just a concise way to record what your preferences are over outcomes. If you prefer some outcome over another, we just encode that by saying you have high utility for that outcome. And so we're not really assuming that people, like we're not really assuming at this point anything about people's preferences, only that they have consistent preferences over outcomes. Now, of course, when we start studying actual games and trying to make predictions within those games, the modeling decisions that we have made in those games in deciding, for example, who the players are, what the action sets are, and what their utility functions are. Okay, those modeling decisions will have content about how we believe the world might work, but the framework itself does not. Just because we use the language of maximizing utility, that does not mean that we are making the assumption that people care only about themselves and not about others. That would be an assumption that would be made by a particular choice of utility function and not by a different choice of utility function. Okay, does that make sense? Questions about this? I mean, I guess it's like you guys are already registered for the class, so it's like, who are the people who showed up? I guess either you sort of think game theory is not just for sociopaths, or like you're fine with that. Like maybe that's what like caused you to sign up. Okay. So what is the general idea? Right, we're going to try to take games and we're going to try to like think about different ways in which we might predict what might happen in those games. Okay, and the general idea is that, all of this we'll need to formalize, but like, in stable situations, whatever that means, all of the players should be playing a best response. Okay, so if we're sort of imagining that, the world is messy, people are gonna, start playing these games, it'll take some time probably for people to figure out what they're doing, for play to stabilize. But like if that ever happens, if play like stabilizes and people are sort of consistently doing something, then in stable situations, everyone should sort of be playing a best response. They should be more or less playing the action that maximizes their utility given what everyone else is doing. And it's sort of tautological. I mean, like, if that weren't the case, then the situation would sort of, if people had even a little bit of cleverness, would not be stable, because there would be people there who would look around and say, look, given what everyone else is consistently doing, because we're supposedly in this stable situation, I am doing something that is suboptimal according to my preferences. So I should change what I'm doing. But if people start changing what they're doing, it's not a stable situation. Okay, so like, so far, a statement like this is sort of agnostic to whether there are any stable situations. Like maybe, play just never stabilizes in one of these games. But if it ever does, if we ever reach a stable situation, then like, it seems reasonable, at least, in English, before we try to like write this down in math, that everyone should sort of be playing a best response because to each other, because if that wasn't the case, it wouldn't be stable. Okay, so that's maybe sort of like high-level guiding idea that's going to be behind a lot of the particular solution concepts that we talk about today and over the course of this class. Okay, questions about this general guiding principle? Okay. So what do we mean by stable solutions, and like, when can we assert that they exist? So in general, what makes it hard to think about what action you should choose if you are a player living within a game is that your utility depends on what other people are doing, and therefore what your best response is depends on what other people are doing. And so if you don't already know what other people are doing, it might be hard to think about what you should do. But if you're lucky, like, you might find that there are like some actions that you can eliminate right off the bat that just like never really make sense. Okay, because maybe there's some other action, some other fixed action that no matter what other people do would always be at least as good and would sometimes be better. And if we do have such a pair of actions, A and A prime, such that A is always at least as good as A prime and sometimes better, no matter what everyone else does, we say that your action A weakly dominates your other action A prime. Okay, so what it means is no matter what everyone else does, you might not know what everyone else is going to do. There's no situation in which it's better to play A prime than A. And sometimes it's better to play A than A prime. Okay, so writing this down a little bit more precisely, if we say that A weakly dominates A prime, that means that no matter what everyone else does, for every profile of actions that might be assigned to your opponents, the other people in the game, if I look at the utility that I get by playing A, and I compare that to the utility that I get by playing A prime, I always get higher, at least as high utility playing A. And I'm not always indifferent. Like, there's at least something that could happen that would cause me to strictly prefer A to A prime. Okay. So like, if that's, I won't always have weakly dominated actions, but if I do have a weakly dominated action, like, I really should, and I have any uncertainty at all about what other people are going to do, like, I probably shouldn't play it. Right? Like, if I'm considering should I play A prime, I should like realize once I notice that I also have this action A, that like any situation in which I would have considered playing A prime, like I should just play A instead, because it'll always do at least as well, and sometimes it'll do better. Okay, so when I'm thinking about what other people might do, well, so first of all, when I'm thinking about what I should do, I probably shouldn't play dominated actions. And when I'm thinking about what other people might do, maybe I should guess, if they're paying attention, that they're not going to play dominated actions. Okay. The reason is because there are no situations in which a dominated action is a unique best response, and there are situations in which it's not a best response at all. Okay. So, we can talk about, for pairs of actions, A and A prime, it might be that A dominates A prime. Though that doesn't always happen. Here's something that's sort of even less common, but really makes strategic thinking easier if the game that I'm playing in happens to have this property. I might have some action A that weakly dominates all of the other actions. Right? I might have some action A that weakly dominates all of the other actions, which means no matter what everyone else does, I know for sure that A is going to be a best response. Right? If there's never any situation in which any of the other actions are better than A, that's what it means that A weakly dominates every other action. Right? So like normally, the thing that makes it hard to think about how to behave in a game, it's that I don't know what other people are going to do, and what my best response is depends on what other people are going to do. So I need sort of some kind of theory of mind for what other people are going to do, right? But if I happen to have a dominant strategy, and I don't care what other people are going to do. It's sort of clear how I should play if I want to be playing a best response given what other people do. It's to play the dominant strategy. Okay, so having a dominant strategy is a very strong guarantee. It's always a best response. It's always the best thing I can do given what others do. And it eliminates this sort of need to have some theory of mind for my opponents. It eliminates the need for any kind of like counter speculation and understanding of what they're going to do. If I just want to concern myself with what I should do that will maximize my own utility. Okay. So, okay. Generally, dominant strategies don't exist. You have to be really lucky to be playing in a game where a dominant strategy exists. And, even less frequently will dominant strategies exist for every player in the interaction. But, if we sort of buy this philosophical premise from a few slides back that in any stable situation, all players should be playing a best response to one another. If we happen to find ourselves in a situation in which every player in the game has a dominant strategy, okay, then it's easy to predict what's going to happen. Then there's sort of there's a clear, stable solution, and that's when everyone plays their dominant strategy. Okay. If there's anyone who's not playing a dominant, their dominant strategy, then they're not playing a best response. They're sort of leaving utility on the table. So, okay, here's our sort of first and most restrictive notion of a stable game state, of an equilibrium. Okay, we'll see a bunch of these. This is the most restrictive, but we will say that an action profile, a choice of action for each of the n players, is a dominant strategy equilibrium. And let me just, since this is the first example of these we're seeing, let me just sort of take note of the type of these objects. The kind of objects that could or could not be an equilibrium of some sort is an action profile, a vector of actions, one for each player. Okay, so a particular action profile is a dominant strategy equilibrium for a game if simultaneously for every single one of the players, the action they are playing in that profile, AI, is a dominant strategy for them. Okay? Does it make sense? Is it clear what we're talking about here? Okay, so prisoner's dilemma, which we talked about last time, is probably like the simplest example of a game that has a dominant strategy equilibrium. So last time I wrote out prisoner's dilemma in terms of, like number of years spent in jail, and you wanted to like minimize the number of years spent in jail. It's like abstract away the story and forget like years. I'm just writing out the same strategic interaction in terms of utility. Okay, so larger numbers are better now. You prefer to be in higher utility states. And remember how to read a table like this. This is how we would write down like a 2-player game with, in this case, 2 strategies for the row player, 2 strategies for the column player, and an entry in this matrix corresponds to 2 numbers. The first is the utility for the row player. The second is the utility for the column player. Okay, and any game matrix that has the same best response structure as this one is called a prisoner's dilemma. Like the story doesn't matter, or the specifics of the numbers. Okay, so you can like stare at this thing and like observe that confess is a dominant strategy for both players. Okay, what is that? What do we have to like check to like verify that confess is a dominant strategy for both players? Well, we have to check that no matter what the other player does, confess is a best response for me, no matter who I am. Okay, so let's think, I'm deciding whether I should confess or stay silent. I don't know whether my opponent is going to confess or stay silent, but I can just go through the case analysis. Maybe he's going to confess. Well, I could stay silent and get utility 0, or I could confess and get utility 1. So the best response here is to confess, because more utility is better. Or maybe he could stay silent. I could stay silent and get utility 3, or I could confess and get utility 5. 5 is better than 3, and so if he plays silent, confess is also a best response. Confess is a best response in both situations, right? So no matter what he does, which means it's a dominant strategy. And the game's symmetric, so he can go through the same reasoning. And for him, confess is also a dominant strategy. Both players have a dominant strategy. And so the game profile, the play profile, which in this case, there's only 2 players, so it specifies an action for each of the 2 players, confess, confess, is a dominant strategy equilibrium of this game. And it is the only stable state in the sense that if we find ourselves in any one of these 4 game states and ask, what happens if we let one of the players change their action so that they are playing a best response to their opponent? Confess, confess is the only one that doesn't have anyone change their action. Right? Anywhere else, right? If we find ourselves in silent, silent, or confess, silent, or silent, confess, we'll have one of the players wishing that they could change their action from silent to confess. And so these are not stable solution concepts in the way that confess, confess is. Right? If we sort of draw out the play trajectory here by drawing little arrows between game states where they sort of correspond to a single player changing their action to a best response, we'd get like a little graph here, and confess, confess would be like a sink of that graph. Nobody would want to change, and the others would all have outgoing edges. Okay, so if we think of play, we'll talk about this more later, but if we think of play somehow as traversing this graph where people are sort of changing their action when they have an opportunity to do so to improve their action, like the flow of where you go would inevitably converge to the dominant strategy equilibrium in this game. Okay, so this is like the absolute simplest example of a game that has a dominant strategy equilibrium. Does that make sense to everybody? Okay. So like, okay, like if we find ourselves in a game that has a dominant strategy equilibrium, like that's a pretty plausible prediction. But things have to like align just right for everybody to have a dominant strategy. So like we shouldn't stop there, right? Like we're not going to be able to make predictions in very many games if the only thing we know how to predict is dominant strategy equilibria. They generally don't exist. Still, right? Like we can use the idea of dominance to try to say something about what will happen in the game, right? Like I might not have a dominant strategy, but I might have some strategies that are dominated, and maybe I shouldn't play those. And if I think you're reasonably clever, maybe I should think that you're not going to play your dominated strategies, which might change what I want to do. And sometimes after I go through the exercise of eliminating the dominated strategies for myself, saying I'm not going to play those, they're dominated, and also eliminating your dominated strategies, I'm saying you're not going to play those, they're dominated, and I look at the subgame that results, in which I've now removed some actions, right, under the presumption that you all won't play dominated strategies. It might be that in this new subgame, some more stuff has become dominated. And so I could continue this process, and maybe if I'm lucky, this would iterate down to a unique prediction. And so we can consider sort of a algorithmic process of iteratively eliminating dominated strategies. And if we're lucky, I mean, this won't always happen, but if we're lucky, it might be that this iterated elimination of dominated strategies, even when nobody has a dominant strategy, nevertheless results in a single surviving play profile. And we can think about, what that might tell us about that play profile. If it's a plausible prediction, maybe not always. You guys just played guess 2/3 the average, and the winning guess wasn't 0. But maybe sometimes, and maybe we can think about relationships between strategies that survive the iterated elimination of dominated strategies and other sensible solution concepts that we have yet to define. Okay, so now I need the ability to draw on this thing, and my computer, the way to do it is to press Shift-D exactly 5 times, but it didn't work here. So let me try something, which is just to go to this ugly view and manually select draw. Okay. Okay, so here's an example. It's like a 2x4 game. I want you guys to help me out. First, observe that, okay, so first of all, there's the row player. They've got 4 actions, A, B, C, and D. There's the column player who's got 2 actions, X and Y. And we can observe that nobody has the players don't, there's no dominant strategy equilibrium. Okay, nevertheless, there might be some actions that are dominated. Can anyone tell me some actions that might be dominated? Yeah. Okay, C and D. So you're saying C is dominated by D. Yeah, like why would I ever play C? Like, by playing D, I'd get like 4 instead of 2 in one situation, or 5 instead of 4. So I really shouldn't play C. Let's cross out C. Okay. And so like the column player probably, knowing that I'm a clever fellow, knows I'm not going to play C. And so, from everyone's perspective, this is the game now. Anything else dominated in this game? Yeah. Yeah, good point. Like, why would I ever play B? Like I could get, or it's dominated both by D and I guess also by A, right? Like B just sucks. Like I could get 5 instead of 3 or 4 instead of 3. So I shouldn't play B. Okay, so like everyone knows I won't play B or C. Now what? In the back. Let's see. Yeah, so now Y dominates X because, okay, if the row player plays A, I don't care, 2 is the same as 2. But if the row player plays D, I could get payoff 4 instead of 3 by playing Y instead of X. So Y dominates X in this new subgame. Note that, yeah, so it's Y dominates X. Okay, so I won't play X. And now, the game is very simple. There's only one action for the column player, and now the row player, faces an easy decision if he sort of believes that people won't play all of the strategies that have been eliminated so far. He can play D and get payoff 5, or he can play A and get payoff 4. 5 is better than 4, so he decides, okay, I'm going to play D, eliminate A, which is now weakly dominated, and we have a unique prediction. Okay, so that's sort of a very small example of iterated elimination of dominated strategies. One more time on a more painful example. Okay, yes. It did not matter. It did not matter. And thinking about the specifics of what you can and cannot do will occupy part of your first problem set. Okay. Second, more painful example. So this is just a bigger example. And again, it's going to have the property that there's no dominant strategy. We can't just look at this thing and say, okay, obviously, you know, like there's a single action profile that people are going to play. But nevertheless, we can make progress by iteratively eliminating dominated strategies. So can anyone tell me a dominated strategy? Yeah. Okay, D is dominated by which? Let's see, but 2 is bigger than 1. Oh no, that's good. That's in the right direction. Yeah, so good. 2 is bigger than 1. -1 is bigger than -3. 0 is bigger than -1. 4 is bigger than 1. 0 is bigger than -1. So indeed, yeah, I wouldn't want to play D because C is always at least as good and sometimes better. So let's get rid of D. Okay, appropriately crossed out. Okay, how about now what? How about for the column player? Now that we don't have to worry about the row player playing D, what might the column player think? X, wait, what? X dominates which one? V? Let's see. So indeed, 1 is bigger than -1, 3 is bigger than 1, 4 is bigger than 1, 1 is bigger than 0. So assuming that the row player is not going to play D, X dominates V. Note that if we hadn't eliminated V, that wouldn't have been the case because 4 is not bigger than 6. But reasoning that the row player won't play D, we now have that X dominates V. So we can eliminate V from consideration. All right, now what? Does the row player have anything they might want to eliminate? Yep. B dominates E. So let's see, 2 is bigger than 1, 2 is bigger than -3, -1 is bigger than -2, and 2 is bigger than -1, indeed. So why would you play E? Given the other things we've eliminated, you'd always be better off playing B. Let's get rid of that. Now what? X dominates W. So let's see, 1 is bigger than 0, 3 is bigger than 2, 4 is bigger than -1, indeed. Why would you play W? You could play X way better. Now what? Yeah. C dominates A. Let's see, 0 is bigger than -3, 4 is bigger than -1, 0 is bigger than -2, indeed. A sucks compared to C. Let's get rid of that. Game is getting smaller now. Now what? Yeah. X dominates Y. 3 is bigger than 0, and 4 is bigger than -1. Indeed. Shouldn't play Y. Now it's just a 2x2 game. Yeah. B dominates C. 2 is bigger than 0, and 2 is bigger than 0, so you would not want to play C. Okay, and now the row player only has 1 remaining action, and so the column player can just decide between payoff 5 and payoff 3. No reason to play X and get payoff 3 when you could get payoff 5. So in this sort of bigger example, we again see that although there's, you know, at like sort of the initial round, there's no dominant strategy, like we get lucky. And when we start iteratively eliminating dominated strategies, we get to a unique prediction. Okay. Yes. Good question. You will think about this on the homework. Okay. Now I'll go back to full screen. And claims I'm sharing my screen, so let's go with that. Oh, am I really though? Okay. Okay. All right. So we said, okay, we have these like dominant strategy equilibria. If they exist, we're golden. But maybe they don't. We just saw some examples of games that didn't have dominant strategy equilibria. Okay, well, maybe we can just eliminate dominated strategies. Of course, if we had a dominant strategy equilibrium, iterated elimination of dominated strategies would have, at only one iteration, eliminated everything except the dominant strategy equilibrium. Okay, so if we're lucky, we get, by iterated elimination of dominated strategies, we get to a unique prediction, and we don't have to worry, right? Sometimes this will work even when there's no dominant strategy equilibrium. And we don't have to worry that we've sort of produced two different like predictive theories that conflict with one another, because, which would be a problem, like, it's which one do we believe? But so far we haven't like gotten ourselves into that particular kind of trouble, because if we happen to have a game that has a dominant strategy equilibrium, that will be what is found via iterated elimination of dominated strategies. In fact, in just one round. Okay, but like iterated elimination of dominated strategies is not guaranteed to do anything either, right? Like it might be that nothing is dominated, in which case, like this hasn't like removed anything from consideration. It nevertheless it makes sense to think about and to ask for stable profiles of actions. Okay, so we will say that an action profile, again, a choice of action, one for each of the n players, is a pure strategy Nash equilibrium if simultaneously for every single one of the players, and simultaneously for every alternative strategy AI prime that they might consider playing instead of the action AI they really are playing in this action profile, it should be that deviating to AI prime from AI is a bad idea for them personally. It can't make their utility go up. Okay, or equivalently, it should be an action profile so that simultaneously every single one of the players is best responding to what all of the other players do. Right? So a dominant strategy equilibrium is a pure strategy Nash equilibrium. But you could imagine a pure strategy Nash equilibrium that was not a dominant strategy Nash equilibrium. This is asking for something weaker. A dominant strategy is something that is a best response simultaneously to anything your opponent might be doing. In a Nash equilibrium, every player is playing a best response just to the particular things that their opponents happen to be doing. Okay, does this make sense? And again, like it would be a bummer for our development of this theory if different things we were proposing as ways of making predictions in games came up with predictions that were in conflict with one another. And so here's a claim that you're going to prove on the homework. If iterated elimination of dominated strategies results in a unique solution, it may not, of course, but if it does, then that unique solution has got to also be a pure strategy Nash equilibria. So this is a more general concept. There might be pure strategy Nash equilibria that can't be found by iterated elimination of dominated strategies. But if iterated elimination of dominated strategies produces a unique prediction, that prediction will be a pure strategy Nash equilibrium. Okay, you'll prove that on the homework. But they might not exist either. Okay, so here's an example. It's a simple two-player game. It's called Matching Pennies. Think of this as like the minimal example for a game that doesn't have a pure strategy Nash equilibria. It's basically, two action rock, paper, scissors. Okay, so there's the row player me, there's the column player you. My action set is heads or tails, your action set is heads or tails, and we've got opposing goals. What I would like is to pick the same action as you, to arrange my coin so that the face siding up is the same one you chose. But that's exactly what you don't want. You want to choose the opposite action from me. Okay? So if we both pick heads or we both pick tails, I'm happy and you're not. I get utility 1, you get utility -1. On the other hand, if we pick opposite signs, if I pick tails and you pick heads, or if I pick heads and you pick tails, then I'm unhappy. I get utility -1, and you're happy. You get utility 1. So this is what an example of what we'll study in some more depth later in the class of a zero-sum game. Note that our utilities here always sum up to 0. I have exactly opposite interests to you. I want to pick the same action you do. You want to pick a different one. And like, we're just not going to agree on a pair of pure strategies to play, right? Like, we're not going to agree to play heads because you're going to, if given the opportunity, switch to tails. We're not going to agree to play heads tails because if given the opportunity, I'm going to switch to heads, right? None of the 4 action profiles in this game is stable in the sense that we talked about, in the sense that defines a Nash equilibrium. None of the 4 action profiles in this game has the property that we're both playing a best response. If I'm playing a best response in one of these action profiles, like by definition, you are not, because we have opposite interests. Okay, so there's no pure strategy Nash equilibrium in this game. Make sense? Sometimes there are, yes, sometimes, okay, so this is sort of one problem with pure strategy Nash equilibria. They don't always exist. Okay, so sometimes like it tells us nothing about prediction. In other times, there might be sort of an embarrassment of riches. Like there might be lots of pure strategy Nash equilibria, and just predicting that someone's going to play a pure strategy Nash equilibrium doesn't tell us anything about, or doesn't tell us exactly at least what they're going to do, because there's more than one. So here's maybe like sort of the classic, 2x2 anecdote of game theory that is supposed to illustrate that there can be more than one Nash equilibrium. Here's the backstory. Maybe, my wife and I both love classical music, but I like Bach and she loves Stravinsky. But like we also kind of like each other. So we on the weekend, like we don't want to go to like separate performances. Like we want to like coordinate and go to the same one. But like all else being equal, I would want to go to the Bach one and she'd want to go to the Stravinsky one. Okay, so like writing that down in game form, like if we both go to Bach, I'm like super psyched. I get payoff 5, she gets payoff 1. If we both go to Stravinsky, she's super psyched. She gets payoff 5, I got payoff 1. And if we like somehow like miscoordinate and go to other, like we each go to our own performance, we're both very sad. We get payoff 0. Okay, so which of these states are pure strategy Nash equilibria? Yeah, the ones where we go to the same concert. Both of them are. There's 2 pure strategy Nash equilibria in this game. Right, so it's like, first of all, the 2 game states where we miscoordinate, those are not pure strategy Nash equilibria. In a Nash equilibrium, both players have to be simultaneously playing a best response to what the others are doing. And in these game states, neither of us are. Right, I could make myself happier by switching to Stravinsky, where my wife is. She could make herself happier by switching to Bach, where I am. So both players are not playing best responses. But if we're both going to Bach, okay, like this is my favorite game state, so definitely I'm playing a best response. And my wife would like to move to us both going to Stravinsky, but she doesn't, in this model of the game, have the power to do that. She can only change her own action. So she could like unilaterally like leave and like go to Stravinsky, but that wouldn't make her happier. She'd be there all by herself. So it's not a best response. Like doing that wouldn't be a best response, even though she'd prefer to be in this game state. right? So like this is a Nash equilibrium. We're both playing best responses. And so is this, in which the situations are reversed. The interaction is symmetric. Okay, so there can be no pure strategy Nash equilibria in a game, but also there can be more than one. Does that make sense? Clear? And you can sort of think about, maybe it's like helpful to think about the kind of game dynamics I suggested you might visualize by drawing arrows. We'll eventually think harder about the graph that results. But if you sort of think about these 4 game states as nodes in a graph, and we draw arrows from each game state to other game states that we could reach if one of the players unilaterally deviated, unilaterally changed their action to play a best response, what would we see? We would see that from these diagonal entries, there are 2 outgoing arrows, one up to this game state, the other to this game state, because I could deviate to playing Bach, to going to see Bach, which I'd prefer, and my wife could deviate to going to see Stravinsky, which she'd prefer. Okay, so from these 2 game states, we'd have pairs of outgoing arrows to the 2 diagonal game states. But these 2 game states would both be sinks. They'd have no outgoing arrows to any state other than themselves. So if you think about, initializing play at one of these game states and letting people best respond whenever they have the opportunity to, this is some dynamic where play is moving along this graph. And I don't, whether we end up here or here depends on where we start and what the order of play is. We don't have anything strong at the moment to say where we'll end up, but like, for sure, this dynamic will end up at one of the sinks of the graph. Okay, everything clear so far? Okay, so like we've been thinking about this sort of hierarchy of predictions. We started with dominant strategies and dominant strategy equilibrium. Pretty good prediction when they exist. They're unique. You can't have 2 dominant strategies. Okay, so like, if we're playing a prisoner's dilemma, maybe we know what prediction to make. And then we sort of generalized that. We sort of said, okay, we can maybe use the same logic. Like we ran into this problem, dominant strategy equilibria don't always exist. So we want to do something more general. We talked about iterated elimination of dominated strategies. And of course, that's only more general. It results in a dominant strategy equilibrium. It finds one whenever one exists. But sometimes, as we saw examples of, it can find a unique prediction even when there are no dominant strategy equilibria. So it sort of expands the class of problems that we know how to make some kind of prediction about. Okay. And then we defined a pure strategy Nash equilibrium, which can exist even more generally when there can be games that have pure strategy Nash equilibria, but for which iterated elimination of dominated strategies does not find them. This is an example. Nobody has any dominated strategies in this game, so iterated elimination of dominated strategies will halt immediately, having provided no insight at all. Nevertheless, it has pure strategy Nash equilibria. And we claimed, didn't prove, you're going to prove it, but we claimed that, again, this is only a strictly more general kind of prediction in that when it happens that iterated elimination of dominated strategies works to give us a unique solution, it'll happen that that solution is a pure strategy Nash equilibria. So we're not getting conflicting predictions. But, again, we have this problem of non-existence, right? Like they might not exist. And so it doesn't give us any kind of, universal way of thinking about what might happen in a game, because suppose we have a game where there are no pure strategy Nash equilibria, what then? Okay. So the question is, can we like generalize this even further in the same style, where we sort of want to think about kinds of predictions that that capture the previous kinds of predictions when they exist, but also more general things. So just to give a definition, for now, you don't need to know much about these. We'll think about them in some depth later in the class. But a two-player game is zero sum if it kind of looks like rock, paper, scissors or matching pennies. If the two players have exactly opposing interests, if for every game state, my utility for that game state is exactly the negative of your utility for that game state. Okay, it's called zero sum because if we sum up our utilities, they'll sum to zero. And of course, like, when we think about, this is something that, just foreshadowing a bit, I mentioned these, sort of best response graphs a few times. It's really only the best response graph that matters in sort of thinking about a strategic interaction, not the like actual numbers themselves. So like, by the way, it's not important that these utilities sum to zero, like they could equally well sum to 5 or sum to 12 or whatever. The point is they all sum to the same thing. Any change in game state that makes things better for me makes things equally worse for you. That's a zero sum game. Okay, so matching pennies is a zero sum game. And this is sort of a class of games that tends to be sort of like resistant to pure strategy Nash equilibria, because, why would we agree on playing, two pure strategies, two deterministic strategies, if the game is non-trivial and I've chosen which one to play because it's better for me, so probably because it was worse for you. But we know how to play such games, right? So like, how would you actually play matching pennies if you had to like play it for money? I wouldn't want to be predictable, right? Like I want to pick the same action as you, but I know you want to pick the opposite action as me. So if you knew what action I was going to play, if you could, guess with any advantage over random guessing what action I was going to play, if I'm more likely to play heads, then you're going to play tails, and that's going to be bad for me. So the way to play matching pennies is to try to be unpredictable, to randomize, to uniformly at random pick heads or tails. It's the same for rock, paper, scissors, right? Like, it sure seems tempting to play rock because rocks are big and they smash things, but right, why would you play paper? But like actually, like, playing rock more than a third of the time is a really bad idea in rock, paper, scissors because it makes you predictable and therefore exploitable. Right? If I play rock more than a third of the time and you know that, you should play paper. And so also in rock, paper, scissors, the thing to do if I'm playing against someone clever is to randomize. And so far, we just don't have a language for thinking about that. Right? Like, pure strategy Nash equilibria it's a label we can attach to an action profile, which as we've discussed it so far, just corresponds to like a deterministic choice of action for each player. Okay, so we're going to need to generalize that if we're going to want to think about games like matching pennies or rock, paper, scissors. And so, okay, an action, this is what's sometimes called a pure strategy. By contrast, a mixed strategy is a probability distribution over actions. It's something I might do if I'm allowed to randomize. Okay, so a mixed strategy is just some probability distribution over my set of actions, which I'll write as, delta AI. This is supposed to evoke an image of the probability simplex. But, it's nothing mysterious. It's just a set of numbers, one for each action, each of my actions that I can interpret as probabilities. So they've got to be non-negative, right? It doesn't make sense to play rock with probability minus 2%. Right? It's got to be non-negative. And they've got to sum to 1. Okay, if I have some way of assigning numbers to actions that are non-negative and that sum to 1, I can interpret those as probabilities. And that vector of actions I will call, that vector of probabilities is something I will call a mixed strategy for me. You could have a mixed strategy for you. Okay, so just as we could think of an action profile, which assigns a choice of action to each of the n players, I can think of a mixed strategy profile, which is a vector in the Cartesian product of the set of probability distributions over actions, one for each player. So it is a mixed strategy profile. It is just an assignment to each of the n players of a probability distribution over their actions. Okay. Now, similarly, utility functions as we've defined them, right? Like, what do? They take as input action profiles and they output numbers, how happy we are with those action profiles. So we need to extend that definition to probability distributions. What's my utility if I and others are randomizing over our actions? And we just extend it by taking expectations. Okay, so I can talk about my utility at a particular profile of mixed strategies where everyone's randomizing over their choice of action. And this is just my expected utility, where everyone, what's the expectation over? It's the expectation over the experiment where everyone selects according to their own mixed strategy, according to their own probability distribution over actions, a pure strategy, an action. Okay, so if we all have probability distributions over the actions we intend to play, like I'm going to play rock, paper, scissors, each with probability 1/3. You really like scissors because they're so sharp, so you're going to play scissors 2/3 of the time and rock the other 1/3. Now I can figure out, given that I know the payoffs for every pure action profile, I can figure out what is my expected utility. Right? It's the expected utility when I randomly sample an action, from this uniform distribution, and you sample an action from this 2/3, 1/3 distribution. Right? That's some well-defined thing. And that's how we're going to think about people's utilities when there's randomization. So that is, by the way, not without loss of generality. Assuming that people are going to be expectation maximizers when there's randomness is something, I'm making some assumptions about how they think about risk, right? You might not really be, assumptions like this are sometimes called risk neutrality assumptions. You just want to maximize expectations. You don't care about variance. So there are scenarios where it doesn't make sense to model things like this, right? I sort of defended utility functions as being very general when we were talking about pure strategies. Here, even just in defining things this way, I am making some modeling assumption here that's not always appropriate. That right, people might not care about expectations; they might be risk averse. But let's think about things this way for now. Okay, so does this make sense? So we can think about randomness now. We now have a language a language to describe strategies that people might play in games that involve flipping coins, right? That involve randomizing, like in rock, paper, scissors. And so we can extend our collection of solution concepts that sort of are all trying to get at this same idea that in stable situations, everyone should be best responding to what their opponents are doing. We can extend that to mixed strategies. Okay, so rock, paper, scissors, it has no pure strategy Nash equilibria, right? Rock, scissors, no, not a stable situation. But we can now define a mixed strategy Nash equilibrium. Okay, what is it? Well, the kind of object that a mixed strategy Nash equilibrium is a vector, a profile of mixed strategies. One mixed strategy, one distribution over actions for each of the n players. And we now know how to talk about utility for each player at a mixed strategy profile. It's just their expected utility when actions are sampled from their mixed strategies independently. And extending our definition in a natural way, we will say that a collection of mixed strategies is a mixed strategy Nash equilibrium if simultaneously, this should say I, not one, if simultaneously everyone is playing a best response within the set of mixed strategies now, that no matter what action I might consider deviating to, instead of playing my mixed strategy PI, maybe I consider playing some action AI instead, is not a good idea. It'll only lower my utility, it won't raise it. There's sort of like an asymmetry in this, the way I've written things here. You might wonder, why am I considering only deviations from playing some mixed strategy PI to playing a pure strategy AI? Why would I only consider deviations to playing a pure strategy? I could have equivalently written, look, there should be no other mixed strategy that would allow me to improve my utility. But I want to highlight one sort of structural observation that's going to be useful to understand, which is that it might be that for strategic reasons, at equilibrium, we need to randomize. Right? Like in rock, paper, scissors, the only stable state is that we're going to play rock, paper, and scissors sort of with uniform probability. But if I view my opponents as fixed, if I think of what everyone else is doing as fixed, and I think to myself, what is the thing that I could do that would maximize my utility? What is my best response? I always have a best response that is a pure strategy. I don't need to randomize to just best respond. Right? Like, and what's the reason for that? Well, what is my utility for playing a mixed strategy? It's just my expected utility. It's my average utility averaged by the probabilities that I put on each of my actions of my utility for playing each of those actions against what my opponents are going to play. And an average can never be larger than the largest number that you're averaging. Right? So I always have a best response that is a pure strategy. Right? Like if you tell me you are going to play rock a third of the time, paper a third of the time, scissors a third of the time, then rock and paper and scissors are each themselves best responses for me. Right? Like if you're not gonna change what you're doing, you're just gonna uniformly randomly play rock, paper, or scissors, I will do as well as I can just by playing rock deterministically. Right? The only reason it's a bad idea to play rock deterministically is because you might change what you're doing to exploit that. But if you're fixed, I might as well just play rock. And so here, when we're sort of saying, okay, fixing what everyone else is doing, I can't improve my payoff by playing any other pure strategy. That in particular implies that I can't improve my payoff by playing any other mixed strategy. Okay, so a mixed strategy Nash equilibria is just a set of mixed strategies, a set of probability distributions, one for each player, so that everyone is simultaneously playing a best response to what everyone else is doing. But now in this world where we've expanded our notion of what a strategy is to allow randomness. Does that make sense? And the reason these things are called Nash equilibria. Oh, first of all, like once again, we're only generalizing the set of things we're calling stable states. A special case of a mixed strategy Nash equilibrium is a pure strategy Nash equilibrium, right? Like, just playing rock 100% of the time, that is a probability distribution over my actions. It's not a very interesting one, but it is a probability distribution. I play rock with probability 1, I play scissors with probability 0, I play paper with probability 0. So a pure strategy Nash equilibrium is in particular a mixed strategy Nash equilibrium. This is only a larger set of objects, but there's more now, right? Like matching pennies, rock, paper, scissors, they don't have pure strategy Nash equilibria, but they do have mixed strategy Nash equilibria. And the reason these are called mixed strategy, the reason these are called Nash equilibria is because what John Nash proved in his PhD thesis, you might have seen a movie about, is that it's not just these examples of games we've seen, but in fact, in every single game that has a finite number of players and a finite action set, and these caveats about finiteness are important, and that you're going to explore on the homework what happens when they're not necessarily finite. But if the game is finite, it is guaranteed to have a mixed strategy Nash equilibrium. Okay, so this is finally, we've starting from dominant strategy equilibria and expanding outwards. We've gotten ourselves to a solution concept, a notion of stability in which everyone's best responding to everyone else, that at least in finite games is guaranteed to exist. Okay, they might be hard to find. There might be more than one of them, but at least we don't have this problem that they don't exist. Okay, and that's going to be the starting point, our starting point in this class. So the proof It's a fixed point argument. It's non-constructive. And so, you know, like they exist, but how do you get there? You know, that's a question we're gonna concern ourselves with for the first bit of this class. Like, you know, okay, like, you know, these Nash equilibria, they're predictions, they're non-vacuous, they like always exist, but like they're not necessarily computationally plausible. So like one of the first questions we're gonna investigate over the first, you know, maybe section of this class is when they are computationally plausible. Like when are there stories of game dynamics we can tell ourselves that will convince ourselves that like reasonable people doing reasonable things will in a reasonable amount of time actually arrive at these stable states. Okay, so that concludes lecture 2. See everybody on, well, see you guys next class. I may have jury duty on Thursday. I'll let you know.